Yeah. So this, remember our goal, we want to apply Laplace transforms to solve ODE. When you have an ODE, yeah, the first thing you need to apply Laplace transform on derivative of that y function, the solution function. So we need to get a formula first. Yeah. It's pretty easy. Yeah. Recall, yeah. So that's the view we learned last time. Operational calculus. Yeah. This point of view. Operations of calculus, derivatives, integrals. What do you do? Derivative integral, that's operations of calculus on functions, are replaced by operations of algebra on transforms. When we apply Laplace transform on these functions, then we change the operation of calculus work to operations of algebra work. That will be much easier. Yeah, so that's what we learned last time. Now we will complete the whole story. Yeah. So last time we learned the theoretical part, right? The definition of Laplace transform, and also we get the basic formulas for Laplace transform on relatively simple functions. So when we went through that list of functions, and we talk about existence and uniqueness questions about Laplace transforms. That's last time. This time we will do calculation part. We will focus on, mainly calculation. The first important theorem is we calculate Laplace transform of the derivative of function, this formula. Okay? Yeah. Second derivative, Laplace transform of the second derivative, that formula. Okay? So this theorem tells us that. Yeah. Next slide, I will derive these two formulas. Yeah. Not very hard. Yeah. Just a few, integration by parts. Yeah. We can get these two formulas easily. Yeah. But before we move to the next slide, I want to explain the bottom part regarding the conditions a little bit. Yeah. Formula 1 holds if f function is continuous on that, semi-axis, right? Yeah, we call this semi-axis. Yeah. All right? Yeah. Satisfy the growth restriction. Yeah. We learned that growth restriction. So here, let me, no. Yeah, I remember I put it here. Yeah. Oh, yeah. If I did, let me write it again. Absolute value of this function less than or equal to some positive m constant times e to the kt. Yeah. That's this growth restriction. Yeah. Yeah, but here growth restriction, the first one, yeah, because the first formula, second formula. So the first formula, the growth restriction on f, right? Yeah. So that ensures that the Laplace transform of f exists. Yeah. So then f prime piecewise continuous. Yeah. And yeah, that condition. Yeah. Yeah, piecewise continuous. Because later we will see if the original function satisfy that condition, then f prime also satisfies that condition. Yeah. So here you can see we do not require f prime function satisfy that growth restriction because we can derive it. Yeah. By the definition of Laplace transform, we can derive it. Yeah. Yeah. All right. So yeah, but here for the second one, now we need to consider actually continuous. Yeah. Here we need right. So here holds and continuous and satisfy. Satisfy that means both, right? Yeah, this one. Yeah. So that. Yeah. But later actually we can derive. Yeah. So by the integration by parts, we can derive. Yeah. Here you can also see, actually you can, from this formula you can also see, right? Yeah. Because if the Laplace transform of f exists, if you want to see if Laplace transform of f prime exists, you just do it first and see if you can get a convergent result, right? Yeah, here from this formula, you get a convergent result. Yeah. So from this formula, you can see the Laplace transform of f prime exists. Yeah. Yeah. All right. Yeah. Yeah. So that's the theorem part. Yeah. After that, so here you can see this theorem tells us one important relationship. That is, here. The first formula, f prime, then you take Laplace transform on the derivative. All right, derivative. Then right hand side the derivative is gone. Yeah, the derivative is gone, but how do you address the difference between the derivative and original function? Yeah, there must be some difference, right? Derivative and original function. Here you can see the difference. The difference is addressed by this S multiplication. S times Laplace transform of the original function. Yeah. This term corresponds to the, Laplace transform of the derivative. Yeah. So that's why we have this view. This view is regarding this Laplace transform operation, differentiation corresponds to multiplication. Okay? Or you say in this way, under Laplace transform. Oh, yeah, Austin Ramy. Admit. All right. Under Laplace transform, the derivative is or becomes, so we know derivative is an operation, right? So the derivative operation is converted to multiplication operation at the other side. Yeah. So this kind of switch, very useful. Yeah, because derivative relatively hard, right? Yeah, we know derivative is very hard to work on. Multiplication, much easier to work. Yeah. So that's the important property for Laplace transform. All right. Proof, yeah. Now we need to prove the formula a little bit. Yeah. Not too hard. Integration by parts. Let's do the first one. Yeah. All right. By definition, first we apply the definition on f prime. Yeah. So definition f prime. Then integration by parts, right? Yeah. So here, so here I write it out directly. Yeah, because this f prime. Yeah, so here, yeah. When we use the differential way, I noticed some students in this situation, they like to use the variable, right? UV variable. integration by parts. Yeah, some student. So they for any integration by parts, they need to use UV variable. Yeah, but here, if you can, use the differential way, because f prime of t times dt, it is just a d ft, differential of ft. Okay, then so you treat this as u times dv, right? Yeah. And for this case, although you can still use uv, but you use it in your mind, right? You use uv in your mind. Yeah. All right. So u times v, then the integral limits, then minus, because the derivative of this du, there is another minus, right? Minus s e s t f of t. Okay, another minus, but you have two minus, right? That's why plus. You have plus. And this part, that's the Laplace transform. The definition of Laplace transform of f function. And how about the first term? First term, can you see the first term after you insert integral limits? They both, integral limits. Let's look at infinity. Infinity, so here, infinity, we expect to have 0. The infinity, s, infinity is 0, but, so here, you can see. So let me go to the previous slide, because the condition is important. So let me go to the previous, the theorem. Condition, we don't have the condition. We don't specify the condition on that s. So the reason I'll go there, and later you will see that condition. Because think about when t goes to infinity, how do you make e, the limit of this inside part, to 0? So here we expect that to be 0. Because how can you say the limit f of t over this when t goes to 0? So here we need this. Here there is a condition we need, limit t goes to infinity, f of t over e to the st. This one, we need it to be 0. If not, things could be very bad. So think about, if we don't have this limit, think about this f of t, if it grows much faster than the bottom, then it does not converge. Does not converge, you get a garbage. Right? Because infinity, you get garbage. It does not exist. Out of control. So we need that condition. But that condition here, let me, because from the theorem we cannot see it. But later when we do the calculation, some other places, suddenly you'll see that kind of condition comes out. But here we do some preparation. For later, when we see that condition comes out, we can understand why. Remember, we have assumption f of t, absolute value less than or equal to m times e to the kt, right? So now we apply this inequality. Okay? So we can replace this m times e to the kt, put it to the numerator. Then, if you put there to the numerator, under what condition the limit is 0? You compare s and k. You treat both s and k fixed constant. sk fixed constant. Yeah. You need s greater than k, right? Yeah. So here there is a condition s greater than k. Yeah. Now to make this work, we need s greater than k. Yeah. Right. Yeah. Later you will see. Yeah. So some places you will see that condition. Yeah. Otherwise, we cannot apply this formula. Yeah. All right. So if we have that, then we have this formula immediately. Okay? Yeah. Because we plug in 0, e term gone, f of 0, right? Yeah, but it's minus because 0 at the bottom. So it's minus. So we have this minus f of 0. Then the second term, s times the Laplace transform of f. Yeah. That's the formula. Yeah. All right. Yeah. But the condition part, we need to be careful. All right. All right. Now we can calculate. Because after we have first formula, the second formula, we just apply the first formula twice. We get a second formula. Okay? Yeah. So because the first time we apply first formula and we treat f prime as the original function. How about that? We treat f prime as the original function. Then, so at f double prime, just the derivative of f prime. So we can apply that function. S times Laplace transform of f prime minus f prime of 0. Yeah. The first step. Second step, we replace the Laplace transform of f prime at the right hand side by the first formula another time. Yeah. Yeah. Inside this brackets, we apply that formula another time. Then do simplification, s squared times Laplace transform of f. Then, use these two initial conditions. Yeah. The second formula. Yeah. All right. Yeah. Yeah. So we proved these two, so we verified these two formulas. Yeah. Yeah. Regarding the proof, because some conditions. Yeah. For the first formula, we check that conditions. For the second formula, if you want to look at a condition, yeah, you need to do a little more work. Yeah, so here I skip that part. Yeah, yeah, because, tedious work. Yeah. All right. Yeah. Now that this formula, think about if we can do Laplace transform on f double prime, can we extend it to Laplace transform of f to any number of derivatives? Yeah? Any order. But we just keep applying the same formula again and again. Do iterations. Yeah. Here, the first iteration. Yeah. So we, bring down the order of derivatives by 1. Yeah. All right. Second iterations. Yeah. Keep doing. Yeah. Yeah. After simplification, keep doing this. Yeah. Yeah. But at the end, we want to, find some rule. Yeah. The final formula, we want to find some rule. So this is the, final version formula. Although we need to check some conditions. Right? We need to check some conditions. Yeah. Yeah. All right. Yeah, but here you can see. Yeah. This method, Laplace transform, you can apply it to solve higher order. Yeah? In a straightforward way. Higher order ODE in this kind of straightforward way. Yeah. Although the calculation, a lot of tedious work. Yeah. Yeah. Could be very messy. Yeah. 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 But because when in the real world situation, we can use the computer software. Yeah. In this situation, we can use the computer software to for the complicated computations. Yeah. All right. Next, calculate Laplace transform by derivative. Yeah. So I show you one example. Yeah. In this example, yeah, we apply those two formulas. Yeah. Yeah. The goal is to calculate that. Yeah. Although you can calculate directly, yeah. So here, for this kind of questions, usually we may have several methods. Yeah. For the same question, usually we have more than one methods to calculate. Yeah. So here I use one, so practice our previous two formulas. Yeah. But you do not have to use this way, yeah, because you can use other different ways. Yeah. Later we will learn several other theorems. You can use, those theorems to do the calculation. All right. So here, let's practice those two derivative formulas. By definition, it's like this. Right? Laplace transform, by definition. Okay? All right. Yeah. So here, all right, integration by parts, right? Yeah. So this step, okay, yeah. This step, preparation for integration by parts. Okay. So we move the e function inside the differential, d e to the negative s. Then, so we have this, constant part, cancellation. Yeah. So here we calculate it directly, yeah, by definition. Yeah. Yeah. After that, then we calculate another way by the derivative formulas. Yeah. All right. So integration by parts. Yeah. So and these two. Now, first this one. Can you see this first term must vanish? Yeah. The first becomes 0. Yeah. If you look at the limit at infinity, when t goes to infinity, t goes to infinity, because this t, you compare t is a polynomial. This is e function is an exponential function. Polynomial cannot compete with exponential function, right? Exponential grows much, much faster. Sine function is a bounded function, right? Bounded, So then you can easily see the limit at infinity is 0. At 0, you plug in 0. Yeah, it's 0. Yeah. Yeah. So the first term is gone. You can see it easily. So you only need to calculate the second one. All right. The second one, yeah. All right, yeah. So you can calculate, but the second part is still you need to do some work. The first term, sine omega x, Laplace transform, we have the formula, right? The sine, we have the formula, so we can apply. But the second one, this t, yeah. So we need to do some work, yeah. This t, yeah. So all right. Here I leave it there, right? Yeah. So here I just show you, yeah. If you apply the definition directly, there is some hard work here. Some hard work here. Yeah. Yeah. It does not mean you cannot do it. So you need to do, some untrivial work here. Now, let's consider we apply the Laplace transform of second derivative. Yeah. All right. F function. What is that? This is F function. F function, its initial value, f of 0 equals 0. Then let's calculate its derivative. Derivative, this is derivative function. Then you plug in 0 in this derivative function, you get f prime of 0 equals 0. Okay? Yeah? So these both terms gone. Okay? Both terms in this formula gone. So after simplification, you have L f double prime equals s squared times L of f. Yeah? So pretty simple. Yeah? Okay? Not pretty simple. Right? Yeah? All right. That's one formula. We leave there. Next, we calculate f double prime. Calculate f double prime. This is f double prime. Okay? Yeah. The prime, then another round derivative double prime. After simplification, you have this. Okay, all right. Yeah. Then, we need to use our basic formula. Number 7. Yeah. Laplace transform of cosine omega t. This is the formula. Yeah. All right. Then let's apply L of f double prime. This time we apply it on this, this function directly. Apply Laplace function on this function directly. And we use the linearity principle, right? Yeah? We take 2 omega out, then Laplace transform of cosine omega t, we apply formula number 7. That's the first term. Second term, we take omega t out, and inside t times sine omega t is f, original f. Yeah. So here, t times sine omega t, that's just the original function. So we can, use the L of f here. Yeah. So here you can see we get around that complex calculation. Yeah, because if you calculate this integral, it could be very complicated directly. This integral, especially the second part, very complicated. Yeah. And when we use the derivative, double derivative, Laplace transform, we can get around it in a smart way, in a indirect. Here, we do indirect calculation, not direct calculation. Yeah. So how to do indirect? Look at this formula. Okay, all right. For the L of f double prime, we also have another equality, right? Yeah. So let's connect these two equalities. Yeah. So these two equalities, so we get this new equality. Okay, we get this new equality. Yeah. And in this equation, we can solve for L of f, right? We can solve for it. Our goal, we want to find L of f, but here we just solve this algebraic equation for L of f. Yeah? That's the indirect way, because we do not calculate this integral directly. We calculate this integral in an indirect way. Yeah. Here, the result, by solving the algebraic equation. That's not very hard. Yeah? Yeah. So you get the answer. Yeah. 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 So that's here you can see when we use these basic formulas, sometimes we need some creativity, yeah, yeah, to apply these formulas. Yeah. All right. Yeah. Yeah. So that is one example. Oh, yeah. Next, another important Laplace transforms of integrals. Yeah. So first, we learned Laplace transform of derivatives. We treat it as a powerful tool. Yeah. From the previous example, you have seen we apply this tool. Yeah. So this these two formulas as a powerful tool to help us calculate Laplace transform. Yeah. Yeah. And this C.4, it's another tool, Laplace transform of integrals, another powerful tool that can help us calculate Laplace transforms. Yeah. So we have more tools, yeah. Derivative tool and integral tool. Yeah. All right. Let's look at the Laplace transform formulas for integral. Still, we do it by definition, from the definition of Laplace transform. Yeah. First, we know what is the relationship between differentiation and integration. Differentiation, yeah. So they are each other, they are inverse operation, each other, right? Yeah, yeah. Then, for the algebraic side, yeah, that's the calculus side, right? Calculus side relationship. At the algebraic side, multiplication and division, they are inverse operation each other. Yeah. Yeah. Here you can see if we want to find Laplace transform of integration, then we expect to see some division operation related to the formula. Yeah. All right, so let's do the calculation. Let g of x, yeah, so we need another function g of x to represent the integral of f function. Yeah. So when we do the manipulation, yeah, sometimes work on g of x, yeah, so a little easier. Yeah. Then this is our definition, but after this definition, we can see f function is just a g prime function. Can you see that? Yeah. So this relationship, yeah, yeah. So that's the, yeah. What do we say? They are inverse operation each other. Yeah. All right. So this so there is a name for this relationship in calculus. It's called a fundamental theorem of calculus. Yeah. So this result people call fundamental theorem of calculus. So you know how important it is, okay, of calculus. Fundamental theorem of calculus. Yeah. Yeah. All right. Existence, yeah. Yeah, so here, before we apply Laplace transform on it, we want to look at the existence question. First, we assume this, for this inequality to make sure that Laplace transform on f exists. Yeah. All right. Then, we want to see if this condition is given, can we derive that g function? Little g function also satisfies that condition. Yeah. Then we can apply Laplace transform on g function. Yeah. Let's do the calculation. Yeah. So, all right. Simple. Yeah. Inequality. So we put the absolute value from outside integral to inside integral. So less than or equal to. Yeah. All right. Then we can apply this formula. Yeah, we can apply this. Pretty easy, this formula. There you can, because -1, we can skip it, right? So we can, cross out. Yeah. Then we have this. Yeah. The constant here, constant. Yeah. So you can see the absolute value of g function also satisfy the similar form of that function. The constant is slightly different. Okay, capital M over K. This constant is slightly different. Yeah, but the structure the same. So this tells us we have no problem. We can apply Laplace transform on g function. Now, so let's do it. Yeah. Let's calculate the Laplace transform. Yeah. So first so we calculate Laplace transform of f. That is Laplace transform of g prime, and we have the formula, right? Yeah, we have the derivative formula. Here you can see we want to use the derivative formula to help us derive the Laplace transform of the integral formula. Yeah? Because our goal, we want to get the Laplace transform of integral formula. But we use the derivative formula as the bridge. Okay? Yeah. To help us find that integral formula. All right. Let's apply the derivative formula. Yeah, S times Laplace transform of g minus g of 0. Yeah. What is g of 0? Yeah. Here. The g of 0 is gone. Can you see why g of 0 is gone? Yeah. So you go back to the definition of g. G of 0, you plug in 0, so you replace this t by 0. It's 0, right? Yeah. So 0, 0. Yeah. So it's gone. Yeah. So here you have a simplified version. Yeah. So after this step, you can see Laplace transform of f equals s times Laplace transform of g function. Yeah. Now let's do the interpretation. Yeah. Because g function is defined as the integral. Okay? So you have the Laplace transform of integral at the right hand side. Okay? Let's write another step. Yeah. So here we have this formula. Right. This formula, this formula you can see, so if we write another step here, S Laplace transform of integral 0t f of tau d tau. Right? Yeah. So then that's your left hand side. Right? Then you do division. Yeah, because the right hand side, this whole thing is you use capital F of S. Okay, so you divide it by this S to the left hand side, so you get 1 over S times capital F of S. So that's the formula. Okay, so you derive this our integral formula, Laplace transform of integral of original function f. And integral here, you can see at the right hand side, what do? Basically, you just do division by s. Yeah, so simple, right? Yeah. Yeah. Division by s. That operation is so simple. We know when we do integration, it's relatively hard, right? Yeah. Yeah, relatively hard. But it's a Laplace transform. Pretty easy. We just use the capital F function to division by s operation. So we get it easily. Yeah. Yeah. All right. So the second formula, just the inverse Laplace transform version of the first formula. You just write it, right? Yeah. Because in the first formula, you just take inverse Laplace transform both sides. Oh, sorry. Yeah. You just take inverse. Oh, what's wrong? Yeah, it's sensitive. I need to put a cloth to, as a cushion. Yeah. All right. Yeah. So the inverse Laplace transform, you apply this both sides, right? Apply to both sides, okay? And inverse and Laplace together, it's gone, right? Yeah. So that's because you apply the inverse Laplace and the Laplace together, these two operations can be canceled out. So what you have is the integral inside, all right? That integral inside, that's the inverse Laplace transform. Inside parentheses, you have this capital F over S. The second formula, just the equivalent formula of the first one, but the form of the second formula. Sometimes you like to use the second formula. Sometimes you like this version, okay? Yeah, so you need both formulas. Both formulas, yeah, because sometimes the first formula is more friendly. Sometimes the second formula is more friendly. Yeah, based on the situations. Yeah. All right. So we have our basic formula. So it's a powerful tool. Okay. After we learn these two formulas, we have another powerful tool we can use to help us calculate Laplace transform or inverse Laplace transform. Yeah. All right. So let's do another slide, then we take a break. Yeah. All right. And here in this example, we need to calculate inverse Laplace transform, but we need to use some basic formula. Formula number 2, yeah, basic formula. Calculate inverse Laplace transform of this function. Yeah. This function, the numerator, a little relatively complicated. Yeah. But if you look at the structure of the numerator, 1 over s here, see? 1 over s, is that structure corresponds to our previous formula theorem? Yeah, right? So we can do that based on this structure. So here we need to calculate these two. Yeah. First one s, second one s squared. Yeah. Times parentheses, I think. All right. Yeah. So let's do the first one. The second one, after the break, we do it. Here we need to apply this formula because capital F divided by S. So here, can we treat this whole thing as capital F? Yeah. So this as the capital F of S. Then we have this structure, right? Yeah. Then we can apply the integral formula. Okay? Yeah. So in that view, because we apply this formula, we identify the structure, okay, right there. Yeah. But we need to, so here, capital F function should be this one. We can get a little f function quickly, right? Yeah, because this formula, sine, right? Laplace transform sine omega. Yeah, but the numerator there is omega, but we can make it up easily, right? Omega at the numerator. All right. Yeah, so let's apply that formula. Yeah, omega put here. Yeah, but when we have this one version, we need to divide it by omega. Yeah, so little f is this function. Okay. Yeah, apply this formula. Yeah, so, yeah, we just divide it by omega, so we get a little f function. Then we need to do integral operation here on that sine function. Yeah, so integral sine, but this calculation pretty easy, right? Yeah, this calculation pretty easy. That one. So then we can write our final answer. The final answer, integral of that. This is the final answer. Yeah. So this is the final answer. Yeah, because integral of f, that's the final answer. Okay. Yeah. Yeah. All right. Yeah. So the second one. Yeah. So let's take a 10-minute break. After the break, then let's look at the second inverse Laplace transform.